6.2 Quantized Energy and Photons. Although the wave model of light explains many aspects of its behavior, this model cannot explain several phenomena. Three of these are particularly pertinent to our understanding of how electromagnetic radiation and atoms interact. 1. The emission of light from hot objects, referred to as blackbody radiation, because the objects studied appear black before heating. 2. The emission of electrons from metal surfaces on which light shines, the photoelectric effect. And 3. Emission of light from electrically excited gas atoms, emission spectra. We examine first the two phenomena here and the third in Section 6.3. Section 1. Hot objects and the quantization of energy. When solids are heated, they emit radiation, as seen in the red glow of the electric stove burner and the bright white light of a tungsten light bulb. The wavelength distribution of the radiation depends on the temperature. A red-hot object is cooler than a white-hot one. During the late 1800s, a number of physicists were studying this phenomenon, trying to understand the relationship between the temperature and the intensity and wavelengths of the emitted radiation. The prevailing laws of physics could not account for the observations. In 1900, a German physicist named Max Planck solved the problem by assuming that energy can neither be released or absorbed by atoms only in discrete chunks of a minimum size. Planck gave the name quantum, meaning fixed amount, to the smallest quantity of energy that can be emitted or absorbed as electromagnetic radiation. He proposed that the energy, E, of a single quantum equals a constant times the frequency of the radiation. The constant H is called Planck's constant and has a value of 6.626 times 10 to the negative 34 joule seconds. According to Planck's theory, matter is allowed to emit and absorb energy only in whole number multiples of HV, such as HV, 2HV, 3HV, and so forth. If the quantity of energy emitted by an atom is 3HV, for example, we say that 3 quanta of energy has been emitted. Quanta being the plural of quantum. Because the energy can be released only in specific amounts, we say that the allowed energies are quantized. Their values are restricted to certain quantities. Planck's revolutionary proposal that energy was quantized was proved correct, and he was awarded the 1918 Nobel Prize in Physics for his work in quantum theory. If the notion of quantized energy seems strange, it might be helpful to draw an analogy by comparing a ramp and a staircase. As you walk up a ramp, your potential energy increases in a uniform, continuous manner. When you climb a staircase, you can step only on individual stairs, not between them. So your potential energy is restricted to certain values and therefore is quantized. If Planck's quantum theory is correct, why aren't its effects more obvious in our daily lives? Why does energy seem continuous rather than quantized or jagged? Notice that Planck's constant is an extremely small number. Thus, a quantum of energy, h nu, is an extremely small amount. Planck's rules regarding the gain or loss of energy are always the same, whether we're concerned with objects in the size scale of our ordinary experience or with microscopic objects. With everyday macroscopic objects, however, the gain or loss of a single quantum of energy goes completely unnoticed. In contrast, when dealing with a matter at the atomic level, the impact of quantized energy is far more significant. Section 2. The Photoelectric Effect and Photons. A few years after Planck presented his theory, scientists began to see its applicability to a great many experimental observations. They recognized that Planck's theory had within it the seeds of a revolution in the way to view the physical world. In 1905, Albert Einstein used Planck's quantum theory to explain the photoelectric effect, which is illustrated in Figure 6.8. Experiments had shown that light shining on a clean metal surface causes the surface to emit electrons. Each metal has a minimum frequency of light below which no electrons are emitted. For example, light with a frequency of 4.6 times 10 to the 14 hertz or greater will cause cesium metal to emit electrons, but light of a lower frequency has no effect. Section 6.8. The Photoelectric Effect. When photons of sufficiently high energy strike a metal surface, electrons are emitted from the metal, as in A. The photoelectric effect is the basis of the photocell shown in B. The emitted electrons are drawn towards the positive terminal. As a result, current flows in the circuit. Photocells are used in the photographic light meters as well as numerous other electronic devices. To explain the photoelectric effect, Einstein assumed that the radiant energy striking the metal surface does not behave like a wave, but rather as it were a stream of tiny energy packets. Each energy packet, called a photon, behaves like a tiny particle. Extending Planck's quantum theory, Einstein deduced that each photon must have an energy equal to Planck's constant times the frequency of light. Photon of energy equals E equals Planck's constant times nu. Thus, radiant energy itself is quantized. Under the right conditions, a photon can strike a metal surface and be absorbed. When this happens, the photon can transfer its energy to an electron in the metal. A certain amount of energy, called the work function, is required for an electron to overcome the attractive forces that hold it in the metal. If the photons of the radiation impinging on the metal have less energy than the work function, electrons do not acquire sufficient energy to escape from the metal surface, even if the light beam is intense. If the photons of radiation have sufficient energy, electrons are emitted from the metal. If the photons have more than the minimum energy required to free electrons, the excess energy appears as the kinetic energy of emitted electrons. Einstein won the Nobel Prize in Physics in 1921 for his explanation of the photoelectric effect. To better understand what a photon is, imagine you have a light source that produces radiation with a single wavelength. Further, suppose that you could switch on the lights on and off faster and faster to provide ever smaller bursts of energy. Einstein's photon theory tells us you would eventually come to the smallest energy burst, given by Planck's constant times frequency. This small burst of energy consists of a single photon of light. The idea that the energy of light depends on its frequency helps us understand the diverse effects that different kinds of electromagnetic radiation have on matter. For example, the high frequency or short wavelength of X-ray causes X-ray photons to have high energy enough to cause tissue damage or even cancer. Thus, signs are normally posted around X-ray equipment warning us of the high energy radiation. Although Einstein's theory of light as a stream of particles rather than a wave explains the photoelectric effect and great many other observations, it also poses a dilemma. Is light a wave, or does it consist of particles? The only way to resolve this dilemma is to adopt what you might seem to be a bizarre position. We consider that light possesses both wave-like and particle-like characteristics, and depending on the situation, will behave more like a wave or more like particles. We'll soon see that this dual nature of light is also characteristic of matter.